All right, our next presentation comes from Alessandro Rigazzi, research engineer at HPE. He's going to be talking about SmartSim, the open source AI framework for accelerating integration of machine learning and HPC simulation. Welcome. How are you, Alessandro?
Hello, everybody. I'm fine, thanks. How are you?
Excellent. I see your presentation's up. You ready to go?
Yeah. Okay. So you can see it and you can hear me okay. That's important. Okay, cool. All right, then let's start. Thanks, everybody, for the invitation and for being here today. So my name is Alessandro Rigazzi. I'm in Lugano, like Ben is. I work for HPE. I'm a machine learning and AI engineer. And I'm one of the developers and maintainers of SmartSim, which is developed by the Cray Labs group at HPE. So keep in mind, SmartSim is open source. So whatever I forgot to tell you about it or you want to know, you can find it online because it's fully open source and there's no secret. So let's start with what is an inspiration on some kind of a driving quote for us. So the use of AI will require the development and evaluation of a new generation of AI frameworks and tools that can serve as building blocks that can be adapted and reused across disciplines and across heterogeneous architectures. So when I say this was one of the driving quotes for our development, I really mean it, because if you think about when the rise of AI started, let's say more or less in 2012 for this kind of AI, we all thought that the convergence of HPC simulation and AI would be super fast and it will be happening immediately, more or less, because we all saw that there would be a great gain in merging the two worlds into one. But after many years, almost 10 years, we still see a gap between the two worlds. And one of the reasons for this gap is basically a language reason, right? The native languages for HPC simulations are Fortran, C, C++, so what we usually call high-performance languages. There are some simulation codes running on Python for sure, but AI toolkits like TensorFlow, PyTorch run are written mostly in Python and can be used in runtimes, but usually you require a lot of Python code and expertise to use them. And so this creates a division between the two worlds, and SmartSim helps bridging this gap. So what is SmartSim? SmartSim is a library dedicated to accelerating the convergence of AI, analytics, and data science with numerical models. So basically what we aim at is to integrating AI or analytics or also visualization into simulation code without having to rewrite large portions or without having to write an ad hoc solution every time. Because many times researchers that wanted to, for example, use AI in Fortran wrote a version of the AI model which was compatible with Fortran or did some tricks to include the AI framework into Fortran, but that is not flexible. And at the next iteration of the AI frameworks, the code will have to change. And if you want to change the model, you will have to change your Fortran code. Instead, with SmartSim, we can keep the two worlds separated when you develop, but then we can merge them basically at runtime. And some usage possibilities of SmartSim are, for example, again, to embed calls to machine learning models into Fortran, C, and C++, but also to execute, monitor, and analyze simulations in, for example, a Jupyter notebook or another kind of Python-based or whatever language you choose to analyze to have an analysis framework. It allows you to easily communicate numerical data and also some sorts of metadata between C, C++, Fortran, and obviously Python. And it does not only work inside your application, but it will also help you deploy your application and executing ensembles, for examples of simulations on your cluster or supercomputer. It will help analyzing data streamed from simulations in real time, and it will do all of this bypassing the file system. Why am I saying this? Well, one of the first attempts we always make when we want to have two or more applications communicating, especially if they come from different worlds like HPC simulations and AI, is to write intermediate files as an exchange medium. So basically, the simulation will write some files, and then the AI model will read them, use them, and then maybe put something back on the file system. And we want to avoid this because this is not what a file system is thought for usually, and this is not efficient. Right? We want to do everything in memory, and we do this with SmartSim and API. So before I go on defining the architecture, just when I talk about simulation models, I talk about any kind of simulation model, right? So basically, SmartSim can be used to enhance any kind of simulation, for example, chemistry, fluid dynamics, oceanography, climatology simulations, and so on. So we have examples for example, OpenFOAM, MOM6, LAMPS, OpenMM, for example. So, and the code base of examples is growing with time. So we really have no limits in terms of simulation domain. So let me give you a picture, a high-level picture of the architecture. So imagine this is your cluster with a workload manager. So basically, it can be Cetonix, so supercomputer running a workload manager, and you start SmartSim. You want to start your typical workflow in SmartSim. So the first thing SmartSim will do will be to launch on some nodes a Redis database. So Redis database is an in-memory database. So it will spin up on the nodes, and it will keep in the memory of the nodes whatever you put in it. So it's a persistent database where you can basically put your data. And this will be running on one or several nodes. And it will also run inside the database the PyTorch, the Onyx, and the TensorFlow runtimes. So this means that the data into the database can be modified and can be used as input to machine learning models. So PyTorch and TensorFlow, we know most likely are going to be AI and neural networks models. But Onyx has flexibility and gives you also the possibility to use the machine learning, like scikit-learn algorithms. And on the other side, SmartSim will launch your native parallel HPC simulation, which will be written in C, C++, Fortran, or even in Python. And this will be parallel, running on several nodes. So you will have these two worlds. On the right-hand side, you see AI and machine learning, and on the left-hand side, you see your typical HPC simulation. And SmartSim will bridge the gap, so will allow you to communicate between these two worlds through SmartRedis, which is our client written for Redis. And this communication will happen through TCP, and what you will communicate is basically data, so mostly tensors, so basically plain old data, which will be then moved so that it's always on the right shard of the database and can always be used to run in AI models or code scripts, or even just to be accessed from other running applications, visualization, or other simulation environments. And all of this will happen not using the file system. So for sure, you can use the file system for what it's thought for. So for example, storing checkpoints or storing your data for long-term storage, but not for communication purposes. For example, again, to communicate between HPC simulation and AI realm. So there are two components to SmartSim. On the right-hand side, you see what we loosely refer to SmartSim itself, which is the infrastructure library, is what sets up the environment, the work tree, the directories, but also will start the database and will make sure that all the applications launched within SmartSim can access the database. So it will have a Python interface, so the API is in Python. Redis for storage, and then machine learning, deep learning, as I said, we have PyTorch, TensorFlow, and Onyx runtimes. It will help you deploy Ray, which is one of the typical choices for training reinforcement learning agents at scale. It has TorchScript and JIT Python to serialize the model and send it to the database and run it efficiently. And it has interfaces with the launchers, so the classic workload managers like Slurm, PBS, Cobalt, or LSF for supercomputers, or obviously local if you just want to run on your local machine. And by interfacing with launchers, SmartSim will be able to launch jobs, to monitor them, to manage them, so that you are in control of the whole workflow. On the left-hand side, you see the client library, so what we call Smart Redis. This is our own client for Redis, which allows you to send data from and to Fortran, C, C++, and Python, right, to the database. It has Tensor API, so basically tensors are the basic building block of simulations. So these are in Fortran, C, and C++, they will be arrays, and in Python, they will be NumPy arrays. And it has dataset API. The dataset API is a way of collecting several tensors in the same data structure and adding metadata so that it's all kept on the same database shard, when the database is distributed. And then it has obviously AI clients and Redis clients to perform operations on the database from within your code. And so this is a typical use case. Let's say you have a simulation which runs on CPUs. So like on Setonix, maybe you have two different partitions of the system, one with CPUs and one also with GPUs. And you run your simulation on the CPU only nodes, right? So you start SmartSim and you launch the application on the compute nodes. And this application is an MPI plus X based simulation. And then SmartSim launches the Redis cluster. And if you want, you can launch it on a different partition. And for example, on a GPU equipped partition, so that if you run inference and AI, it's faster, and you can run GPUs on GPUs, right? So you will have the orchestrator, which is our database, running on the GPU nodes, and you will have the simulation running on the CPU nodes. And between them, there will be communication going over TCP sockets, right? So you will be able to send data to the orchestrator and run inside the machine learning or AI runtimes. And this TCP communication will be performed through Smart Redis. So Smart Redis will be the code so the calls to Smart Redis will be the ones you will have to include in your code, so your original simulation code to analyze, to send data to the database. And at the same time, you can have an analysis environment, right, running concurrently on other nodes or maybe on your laptop and accessing Smart Redis. So accessing the database to visualize the data you're producing in real time. Smart Redis API, just to give you an idea what the operations are, so the possibilities are. So we have a simple set of data structures, tensors, which are again collections of scalars basically. You can create them, put them on the database, and then access them. Models, which are all the AI and machine learning models, and you can set a model so that it's on the database and you can use it locally, or you can get it back and you can obviously run on the database. And scripts. Scripts are Torch scripts. So TorchScript scripts, which means TorchScript is quite generic way of handling and manipulating tensors. So you can create these scripts, for example, to pre-process your data in memory onto the database. And then you have the dataset API, and this is basically constructs. So you can construct data sets, adding tensors, metascalars, and also strings. You can store, and you can inspect, obviously, the data sets so that you can put them on the database or you can access them from other applications. So let's look at some of the use cases we thought SmartSim for. As I was saying, online analysis. Your simulation produces results, right? This is an MPI simulation. Each rank has a Smart Redis client, which is a very lightweight client, which is just sending data over TCP to the orchestrator. Data is stored on the orchestrator, so it's in memory on the database nodes. And then from an analysis environment, like for example, we say Jupyter because we know that researchers love to analyze their simulations in Jupyter. In real time, you can access the data and visualize it in Jupyter, bypassing to the file system. Or you can do online processing. So let's say you have some function that you can run on the database and you don't want to include into your simulation because maybe it's just some post-processing or pre-processing of the data for the next stage. And so on the right-hand side, you see a code, a complete code of this possible workflow. So you define a function here, which can be something which Torch script can interpret and run, for example. And then you set it with a call to set function so that it's stored on the database and it's executable on the database. And then whenever you have data on your simulation, you can send it to the database and then you can analyze it there. Or you can run your function there and then you can get the results. Or online training, you can have nodes which are running, for example, TensorFlow training with Horovod or a deep learning plugin to train in parallel, and you want to train the models on data which is produced by your simulation. So your simulation will put the data at each time step, for example, on the database, on the orchestrator, and the training service will access this data every time it's produced, and then it will use it to train the model, and then it will store the model on the database so that it's accessible for other simulations or for other applications for inference purposes. And inference, for example, means we have a neural net, we define it, we can have it in another file, obviously, or we can have it stored, and we put it on the database so that it's there, and then we can send data to the database and run inference on the database. And then when the inference is run, we have the inference output that we can access and we can get back from the simulation or from another application or from a visualization toolkit to proceed to the next stage of the workflow. Okay, now let's get to a more concrete use case. This is the latest research paper we published. It was a collaboration with the National Center for Atmospheric Research in Boulder, Colorado. Let me give a shout out to everybody who collaborated to this work because it was a it was a great experience to work with a diversified team like this one. We all came slightly different backgrounds and we worked together and we were able to put together what I think is a very, very good research. And so what we wanted to do was to enhance oceanography simulation with AI. So we didn't want to replace the simulation. We just wanted to enhance it. And why did we want to do this? Well, basically, there is a quantity which is called E, or eddy kinetic energy, and it's an indicator of turbulence for obviously ocean flows and ocean currents. And this quantity you can compute it very well on a fine grid, right? So if you have a high resolution grid, like 1/10 of the nominal resolution, you can resolve this very accurately and you can find E key. But when you go to production, you usually use lower resolution grids, like 1/4 of a degree, for example. And there, the turbulent flow is not resolved at the same level. And so quantities like eddy kinetic energy are different or impossible to compute at that resolution. So what we thought was, why don't we train a neural network on the high resolution data? So on the 1/10 of the degree model, we had a lot of data stored from the NCAR guys, and we could train a neural network. We did this offline. And then when we run the simulation on the coarse grid, we use this neural network to compute the eddy kinetic energy just as inference. So we get the same input we were using to train the neural network on the fine grid, but now it's coming from a low level resolution, so from a low resolution grid, and we use it to compute the same quantity. And what we did then was to send the data from this rank. So this was obviously a Fortran MPI simulation running on 3,500 plus ranks. And we were running this on each rank. There was a Fortran client, so SmartRedis Fortran client, and we were sending data to the database, to each shard, basically, and then getting the results back to the simulation, and then we use those results to compute the next step. Right. This was the basically our typical workflow here. So SmartSim would launch the simulation in parallel, and then we'll launch the database, and there would be this ping pong of data going back and forth from the orchestrator. So sending input in and getting the inference out. And so we were using 4 input features. So the mean kinetic energy on the surface, the isopycnal slope, the deformation radius, and the relative vorticity on the surface. The simulation was running, as I said, on 3,500 ranks, and the orchestrator was running on 16 nodes, which was like on each node we had 1 GPU because this was an XC50, so which was basically the simulation. So the orchestrator was running on 16 GPUs, and on each shard we had an identical copy of this pre-trained model, which is EQ-ResNet, a modified ResNet neural network. And so here is the result. This is a simulation. Again, remember we are doing online training, meaning it's online inference, sorry. So meaning that at each time step, we get the simulation state, we send it to the orchestrator, we perform inference, we get the result back into the simulation and use it to compute the next step. And here it is. And so what you really see is that all these structures here, macroscopic structures, are well-known phenomena like Western boundary currents or equator activities, which were predicted, which are usually measured on the ocean, which are predicted by the theory, but they were not computable with the 1/4 of the degree model. Instead, here using AI, we could enhance the simulation and compute this quite accurately. All right. And so when I say quite accurately, what I mean is that compared to the previous state of the art, we did a great leap. So if you look at the top left corner, this is what we call the truth data. So the ground truth is what we computed on the 1/10 of the degree model. On the top right corner, you see instead the simulation on the 1/4 of the degree model using AI and doing an ensemble average. We'll talk about this later. Whereas on here in the bottom, you see what the previous state of the art was, right? This was a parameterization by Jensen and others. And basically they were using parameters from the model trying to find the EQ values, but they were completely missing the equator activities and they were overshooting in the southern hemisphere. So this was basically, for us and for the NCAR guys, this was a big improvement in quality of prediction. And for the paper, we wanted to do something more. So we weren't satisfied with our simulation, and so we decided to run an ensemble of simulations. So why you run an ensemble? Well, typically it's because one simulation is not enough. You want to know uncertainty of your simulation. You want to know mean values and deviation from the mean. So with SmartSim, if you have the workflow set up for running one simulation, running dozens of them, it's not a problem, right? So you just run an ensemble through SmartSim. Each simulation now was running on 900 ranks because the system was not large enough to run 12 simulations of 3,500 ranks. On each rank, we were running one client instance, right? And so we had 12 simulations, each one running on 19 nodes. The database, the orchestrator, was still of the same size as the previous computation. So basically it was just 16 GPU nodes, right? We simulated 10 years. So we ran on the database more or less 10 trillion inferences. And the slowdown was negligible for the simulation compared to the previous state of the art. So really, we were running an ensemble of 12 instances, and the slowdown was less than 2%. And so every simulation was sending its own state, so its own data to the database, and we would get back the inference. And so the E-key value computed by a neural network on the database. All collisions because of names are avoided by SmartSim automatically. And so really, there is no further mechanics to add to your simulation to run, to go from a simple simulation to an ensemble. And so here are the results. This is another video. On the left, top left corner, you will see the average, and the average will look more or less like the other video I showed. On the top right corner, you see the standard deviation, and on the bottom, we have put 2 members out of the 12 members. Remember, you can do this analysis also online if you like, so you could have just your Jupyter notebook accessing this time step at each frame and rendering them and showing you what's happening in the simulation. And researchers love to know what's going on in the simulation while it's running, because sometimes they want to stop it or they want to steer it so that it goes in the right direction. And here's what we observed, right? So you see where there are high activities, the deviations are higher. And this is also shown in the members where you see higher activities on the western boundaries, and where we know that we would get high activities. And here, so these are obviously the distance to the mean, right? This is not the absolute value of the activity, but it's just the distance to the mean. So here, the turbulence is very high, and the chaotic, basically, nature of the phenomenon is more evident. And yeah, so this concludes the my talk. So remember, SmartSim is completely open source. So if you want to know more, you can just go to the repo. We have the repo for SmartSim, and we have a repo for SmartRedis. Even though if you want to access the database, you will need both, basically. Unless you want to spin up a different Redis database, then you can just use SmartRedis if you really want. We have a repository for the paper. If you're interested, you can find it also on archive. The documentation and everything is accessible from the repo. So if you go to GitHub, you will find the documentation, and you will find a Slack channel invite. So we have a Slack channel for SmartSim. Click on the invite, you will just get access to the Slack channel, and we will be happy to help you using SmartSim in your workflow, in your simulation, or telling you what I forgot to tell you in this talk. And we are always happy to collaborate with scientists, and obviously with labs and supercomputing centers to port their applications to SmartSim. And yeah, that's it. I can take a few questions.
All right. Thank you, Alessandro. I do have one question from Paul. He says, thanks for the talk. For the MOM6 example, would it be feasible to interface to a coupler such as Oasis 3-MCT rather than directly to MOM? That way, ML model output fields could be shared between ocean, sea, ice, atmosphere models.
Yes, this is a very good question. And yeah, we thought about this use case too. And yeah, this is something we can do with SmartSim. We can do this for a fully coupled model. We can access all. Also, if it's you have many different applications running, you can access the data which is stored on the orchestrator from different pieces of your orchestrated application, and this can be done seamlessly. Obviously, you have to put SmartRedis calls in each part of your simulation. But yes, this is something we thought of and SmartSim is thought for. Yes, thanks for the question.
Great. Thank you, Alessandro. That was my last question.